Hello everyone, I'm Lawrence from Extrapy. Welcome to Module 5 of our Smart Contract Auditing course. This module really is at the heart of the course, and in this module we'll be exploring some of the vulnerabilities you may find when you're auditing Cairo contracts. We've split up the topics into 4 areas today. So some of the vulnerabilities are general vulnerabilities you would find in Web3. You may have found these before if you've been auditing Solidity contracts. Then we have some that are more specific to Cairo. Then some are more about the Starknet chain itself. And then finally we have some that are about the messaging between the layer 1 and the layer 2. So let's start with some general vulnerabilities you may find in smart contracts. And you may have come across some of these before. The first one here, lack of access control, is perhaps one of the more important ones. Then we'll look at some unsafe authorization, some particular vulnerability about that. We'll talk about the problems of thinking you may have private data. Then we'll come on to one of the most famous vulnerabilities, Reentrancy, and we'll finish looking at the possibility of signature replays. So to start with, lack of access control. So a very important area. We typically want our functions to have some kind of control over who can access them, particularly if this is going to be any type of critical function. And the one way that you can do this, one way that I like to do this, is to think about the different roles that a user may take when interacting with my contract. Maybe write those down and then check those roles against the functions in your contract and see if those roles are being checked for. And from that you can hopefully spot if you've missed out any access control on a function. So the example code we've got here is one where this has been missed out. We've got a function that is designed to mint tokens, and the way it is written is that there is no access control on that. So this means that anyone could call this function and create some tokens, and that is quite unlikely to be what we actually want to have in our contract. So the way to fix this is quite simple. We just want some code that's going to run at the beginning of this function that is going to check that the person that is calling this function is allowed to call that function. Now this may be actually in the mint tokens function, or perhaps you would put it in another function, but either way we want some kind of check. And we would probably have an authorized user, the address of them stored within our contract. Okay, so the fix for, as you'll see here, is that we do in fact store what we call an owner of the contract. So this is someone with extra privileges. They are allowed to do things such as mint tokens. So we store their address in storage, and then in the function we can check to see if the caller of the function is the owner of the contract. If so, then that's good. We can then go on and allow them to mint tokens. If not, then we're going to throw an error. Okay. Now, unsafe authorization is about some of the context that we have when we are running our contracts. We have some details of who is calling the contract, and specifically who initiated a transaction, and then also who is the immediate caller of a particular function. And we have to be very careful about how we use these, because there is a well-known attack that can happen if we use the address of the person who started the transaction. If we use that for authorization, then it leaves us open to a man-in-the-middle attack. And this is quite well known in Solidity, where we have a variable TX origin, and we have the corresponding thing in Starknet with the account contract address. So the example we have here is to illustrate how this could be exploited. So we have a transfer to function, and we are checking that the person, the caller of this, is authorized to do a transfer. Now, the way that this has been written, what we are doing is we're checking the address of the originator of the contract. So this is the account contract address, as you can see there, and we are setting that to be a variable authorizer, and then we use that as a check to see if that is the same as the owner. If so, then we do a transfer. So the way that this could be exploited is that a malicious user could create an extra contract. It is a man-in-the-middle attack, so this contract would effectively be in the middle of and between the user and our vulnerable contract. In this middle contract, there could be a malicious transfer to function, and our innocent user who is authorized to do a transfer could be tricked into using this contract, calling the transfer to function. And it may not be called that, it may be called something else, and they may have been tricked into calling that, thinking that it's going to do something different. But either way, that malicious extra function could then call our vulnerable contract and call the transfer to function in our vulnerable contract. And the authorization that we would get in our vulnerable contract in this vulnerable function would be that the caller of this function is authorized to call it because the originator is indeed the owner of the contract. But obviously the problem lies in the fact that they call this function via the middle contract that is malicious, and the owner called that not realizing what the end result is going to be, not realizing that they're going to end up calling the transfer to function. Okay, so I give you the flow there, but I hope that that's fairly understandable. And as I say, it's a well-known vulnerability in Solidity, so you can check out, it's a similar type of flow. So if you want to check out that, there's plenty of documentation around that. So that's the problem. So what we need to do is not to use this account contract address, but instead use the get caller address, which is then the immediate caller of our function. And if there was an intermediate contract, a middle contract that was calling our vulnerable contract, then the get caller address would correspond to the address of that contract rather than the address of the original caller, the originator of the transaction. Okay. Now, quite a simple vulnerability here is just the fact that sometimes we have mistaken assumptions, and this really revolves around this keyword private, which some people may be misled into thinking that this means that there is a possibility of private data on Starknet, which is not the case. All of the state on Starknet is public. Anybody can read state, and it's not even the case that we have to have a function returning the value of state. Somebody can construct their own way of reading state using this hash of the not very secret password as we give at the bottom there. So just be aware that even though you may think that by the naming of the keyword that something is private, that is not actually the case, and that all the data on Starknet is public and should be regarded as public. So don't make that assumption. So reentrancy, one of the most famous exploits in Ethereum, and we also have this possibility on Starknet. The fundamental way that reentrancy can work is that it revolves around someone making a call to an external contract. And where this can be problematic is if that call is dependent upon some state, and if there's some kind of permissioning which would mean that we would do the call or we wouldn't do the call, and then this call could perhaps be used to say transfer tokens or update the state in some way. And there was an original, the sort of classic reentrancy, the single function reentrancy, but over time people have realized that there are other variants of this that you need to be aware of. So I'll just talk you through what these look like. The single function reentrancy happens where we have our vulnerable contract C. This has a function F, and then this is going to call an untrusted contract. And what this untrusted contract does is, rather than doing the expected functionality, maybe doing some changing something and then returning, instead what it does is it recalls the function F in our vulnerable contract. And so this sort of sets up a kind of a loop. And this was the well-known, the classic reentrancy. And it is well known. Unfortunately, despite that, and despite the fact that it is easy to guard against, there are still many examples of this being taken advantage of. We get a variant of this, called the cross-function reentrancy, where we have an extra function, G. So our vulnerable contract has the initial function F, and then also have a function G. When we call the malicious contract, what the malicious contract will do is to call the function G rather than the function F. And this will be to take advantage of something that G is able to do. Taking this a little further, we have the possibility of cross-contract reentrancy, where the issue here is that there is some shared state between the contracts, and there is some assumption that this is going to be synchronized, that we're going to have some kind of consistent view of this. And what can happen is that we can do reentrancy in such a way that we don't have a consistent view. Effectively, we have a view of stale data, and there is some assumption in the contract that depends upon this data, and the fact that it is stale could then lead to some kind of exploit. Similarly, we have the idea of the read-only reentrancy, in which case that we have a view function, a read-only function, and typically when we write in view functions, we perhaps are less worried about the control of those, and we wouldn't necessarily be putting guards on those because we know it's not going to modify state. But again, we have this problem that this could produce a view of stale data, and then that view could be acted upon and lead to some kind of exploit. So these last couple of types of reentrancy are all about the fact that there is the possibility of stale data being acted upon, and this could end up with producing an exploit. Okay. So how do we get around this? Well, there are fairly straightforward ways to prevent this, and the first one is to follow a pattern. When you're writing your functions, have the statements within your functions in a certain order so that we will not be vulnerable to reentrancy. And this is called the check effects interaction pattern. So the idea is that we update our state within the function before we make the external call. And this means that external call cannot then rely upon any stale state, and that will prevent it from being exploited. The other way that this can be done is to use a reentrancy guard, and these have been written. They're available from, say, OpenZeppelin. They're a little different to the reentrancy guards you may have seen in Solidity, because these are implemented as components, and what we need to do is we have two methods in them. When we start, we call the start method, and then we call the end method before we do the return statement. This is different to the way that we guard against this in Solidity, because we don't have modifiers in Starknet, so we have to do things a little differently. But there's an example that you can see here to show you how that can be done. So here we've got the component being defined, and we've got within some functions the use of this. So as you can see in this protected function, we call the reentrancy guard start, then we do our logic, and then finally we do the reentrancy guard end. So that will then prevent the possibility of some external contract re-entering into our contract and recalling these functions. And there's a further example here from the Starknet book, where this of a vulnerability, or this being exploited. And what this is doing is the user is creating an asset. They're minting this NFT sword, which they're going to use in the game. And the point is that we get this. There's this onReceive sword function, which can be executed, and this can be used again before we are updating the state to show that someone has already minted their sword. So effectively what they can do is, by re-entering multiple times, they can mint multiple swords, so give themselves multiple assets. So oops, sorry, I don't know what's happened there. Let me okay, so yeah, you can see, if you look through the code, you'll see that the way that they can do that by sorry, let me just make that smaller. Yeah, so they need to show that the sender has already minted the sword, minted this NFT. That needs to be updated before we do an external call. Otherwise, we could get reentrancy. To fix this, simply use the check effects interactions pattern, and that will put the state. If we use that, we will have the statements in the correct order, and then we won't be vulnerable to this. Okay. So moving on to a very different type of vulnerability, the possibility of replay attacks. And the possibility here is that we could take an existing transaction and then replay that and use that to gain some advantage in some way. The way that is guarded against is that we have a nonce in our system, so we expect a nonce to be strictly increasing, and that prevents this type of thing being done. On a particular chain, of course, you could try to replay a transaction on another chain. To prevent that, we have the chain ID. So what we should be doing when we are verifying our transaction, we need to be checking the nonce and the chain ID to make sure that this it hasn't been replayed on this chain, and also that we are on the correct chain. This transaction hasn't been used on another chain. To make this more robust, we also have the idea of domain separators, and this binds a particular transaction to a contract and a function that the this transaction is meant to be calling. So it's a way of fingerprinting a function within a contract, really tying this down so that there's no vagueness or possibility that this transaction could be used for anything else. So there's an example here of this being exploited because we're not using any type of domain separator or nonces, where we've got a signature that was created that is being passed in and being verified as a correct signature, but we're not verifying that this signature hasn't been used already within this chain, or that it does actually apply to a particular contract in a particular function. It's not actually, we're vulnerable to the fact that this could have been used in a different contract and to call a different function. So to prevent that, we should make use of domain separators, so that ties it down and to a specific particular function within a particular contract. Okay. So let's move on then to some vulnerabilities that are specific to the Cairo language. We've got a couple of examples of that. Both are very much concerned with the fact that we have a language that is being used for provable computation, that we are creating zero-knowledge proofs. In order to be able to do that, we are using finite fields, and we're using the fact that we are creating proofs to show that something has been done correctly, and this proof is to show that there is some kind of claim that is being verified. So we'll start with the maths operations, and we face the problem that because we are basing our arithmetic on integers, because we have a limit to those integers, because we have a finite field, this means we're doing modular arithmetic, and this could then produce problems because the modular arithmetic could produce results that we were not expecting. This could mean that we get some type of overflow or underflow. So maybe you will be checking a balance and checking to see that balance is greater than 0. But it could be possible that if we get an underflow, then this check will not work correctly. The best way to avoid these types of problems is to use range checks, to check that the values that we are using are within the range that we are expecting. And this could be quite specific to the functions that you have in your particular application. And you could use some intelligence around this and say, well, I know that if I'm talking about a balance within my particular contract, that this means that the value is always going to be within a certain range, because I know that we've got, say, a total supply, and therefore the balance could never be greater than that. Obviously, that is going to be quite specific to your particular contract if you do that. So the way to get around it is to use some kind of checks. We can also be checking against underflow and overflow against the maximum values of the field as well, to make sure that we're not getting that. So always include these checks if you're doing arithmetic. Another point is around division. This may behave in a way that you are not expecting. So sometimes division will work in the way that we usually think of division working. So we've got the example there that we are dividing 8 by 2, and then this will give us the value 4, which is what we would expect. But if you, for example, divide 30 by 9, the results you get in Cairo is certainly not the type of result that you would expect. So you can see the value there that you would get. And this is because we are using modular arithmetic when we are doing these operations. So when you're doing arithmetic, you need to be checking that the values that you use are sensible, that they lie within a correct range. Another approach that is done in zero knowledge applications is to have the division done outside the checkable, the provable part, and then as part of the proof to check that if we multiply the result of the division by our original arguments, and thus comes up with the correct result. But there are more details about that in the Cairo book. The next point is one that is really relevant to ZK applications and protocols generally, and I spoke a little bit about this at the beginning of this course, and this is the idea of under-constrained code. And when we are using a zero-knowledge proof, we are taking that as proof of a certain claim. And the way that works is that we are providing some program, and the proof really is the proof that program executed correctly. And so what that program needs to do is to verify the claim that we are making. So if I am claiming that I know the square root of 25, then maybe the program will be taking the value that I claim is the answer to that and checking that that indeed is the square root of 25. Now, if I didn't do that check explicitly, or if I didn't do it rigorously enough, then we could still end up with a zero-knowledge proof that would be that could be verified and would seem to be correct. And what that would show was that my program ran correctly. But what it would not be showing is that I know the square root of 25, because my program is not correctly checking that. And so this applies generally. When we are writing our contracts, we need to make sure that all the assumptions that we have are being tested within the contract, so that there's no possibility of a malicious user sending in some input that is crafted in a certain way that will allow the program, the contract to complete and for our transaction to complete, but in a way that shouldn't happen, because we are missing some kind of check that would really should be there to throw an error. So the bottom line for this is that when you are writing your contract, you have to be very rigorous. You have to make sure that you have sufficient checks to show that all of the assumptions you have, all of the claims you're making about, say, the state of your contract are being tested. And these are being tested in your code. And then the proof that we get that is being verified on the layer 1 is going to be the proof that all of these tests have passed. And therefore, the claims, the assumptions that we've got are correct, and that we don't have any possibility of a user doing something malicious. Okay, let me move on then to a couple of Starknet vulnerabilities. So the first one is around upgradability, and when we are upgrading contracts, this works in a different way to it does in Solidity, and you have to be careful when we're doing this that the way that we calculate the location of the storage is by taking the hash of the variable name. And this is the order that we declare our variables within storage. Doesn't matter. It is the name of the variable that is important. So therefore, if we have data within storage in a version 1 of our contract, then we decide to upgrade our contract to version 2, and we expect to still access the same data. It doesn't matter if we change the order of the variables within our definition of the storage. But if we change the name of those variables, then in the version 2 of our contract, we will be looking at a different area in storage. So the original data that we've got will not be seen by our upgraded contract. So you need to be careful if you're doing the upgrade. Just make sure you don't change the names of the variables. Okay, and there's more details given there in a few links. The second point is about low-level calls when we are accessing storage. And we typically are doing low-level calls because we want to do that in an efficient way, and so we can do that with the calls that you can see here, and there's links to the definitions of those given also. So the first one here is where we are reading from storage, and this gives us direct access to the items in storage by as you can see by using the keys that we have for that. We also then we also have this function to do a write, which allows access to any key in storage again, and would allow us to update that. So the problem that we could potentially get is that if we are doing the read and the write, the actual storage of these is going to be computed, and then that is going to be accessed. So if we do a low-level call, there's no validation that the hash that we are supplying is the one that is actually correct. If we're using the read and the write functions, then we've got some guarantees. Whereas if we're providing these directly, we no longer have those guarantees. And the example for this came from the underhanded Cairo contest, where someone submitted an example of using low-level calls in this way to then show that to produce a vulnerability. Okay. So let me move then to the interaction between the layer 1 and the layer 2. And what I'm talking about here is not the sort of typical roll-up interaction, but is where we are messaging, passing messages between the layer 1 and the layer 2 directly. And there are, as you can see, quite a few possible vulnerabilities that we can get if we do this. So the first one is all about the fact that the format of addresses on our two systems is different. On layer 2, on Starknet, we are using the felt, so the felt 252 to store our address. On layer 1, Ethereum, we have a uint 160. It's just a 20-byte address. And so if we are doing any kind of conversion between these, then we have to be very careful that that is being done correctly. One particular point, I suppose this applies generally between when we're thinking about conversion between Solidity data types and Starknet data types, is the fact that the felt is smaller than the UINT256, and therefore, rather than, if we want to use a UINT256, we typically use a struct where it's broken into a high and a low level part. Obviously, that is different than if we are looking at addresses. So when we are doing any kind of conversion, we have to make sure that we are not losing any data, that we are doing the conversion correctly and getting the correct address. So when we send the message from layer 1 to layer 2, make sure that the inputs to that are validated properly. And the relevant point here is that the address that we get should be smaller than the size of the finite field that we have on the layer 2. Okay, and you got an example here of code that's doing that. You can see there's a require statement in the Solidity contract that is doing wants to do the messaging to the layer 2. We have a require statement which checks the address, which is in the 2 field here. We check it against that it's not 0, which is an invalid address anyway. And then we also check that it's less than the maximum size of our finite field on Starknet. And if those 2 checks pass, then we proceed, and hopefully we've got the correct address. Now, the next point we have is when we are going from the layer 1 to the layer 2. And it's to do with the fact that the sequencer is responsible for handling the messages. The sequencer on the layer 2 will know that there is a message wanting to be processed coming from the layer 1, and it is responsible then for getting that message to the correct contract and the correct function on the layer 2. And the a potential problem with this could be that if there was a sudden spike in the gas price, then this would mean that we don't have sufficient gas to pay for this to happen, and so therefore our message effectively would stay in a pending state. The problem is that then we've got a kind of an intermediate state that we don't want. We want to have some atomicity involved in this. And so what we would, a way to get around this is to say that to allow the contract that sent this message from the layer 1 to be able to cancel this message if it is going to still be in a pending state. In this case, we've got the idea that there will be a time interval involved here. So we're saying here we would have 5 days for this. So this would prevent a further problem where we could get the possibility of a denial of service attack, where somebody could send a message, then repeatedly cancel a message, and then send another message, etc., to provide extra work for the sequencer, potentially overload the sequencer. So so that's the possibility. We need to make sure that we can cancel these if they haven't been processed. Again, looking at messages coming from the layer 1 to the layer 2. So the way that this is done is that we call the send message to L2 function on the contract on the layer 1. And you need to make sure that this is going to have sufficient funds to do that. And some of the cost around this is to do with the fact that we need to take the hash of this message. And so that will need to be calculated and registered. And then there will need to be further gas spent for the processing on the layer 2. So you need to make sure when you're calling this that you're putting sufficient way into the transaction that is initiating this on the layer 1. Okay. Again, going from layer 1 to layer 2, when we're doing this, we need to serialize everything into a payload. The format of this is an array of Uint256s on Solidity, and then this array gets passed as an argument in the send message to L2 function that is responsible for getting the message to Starknet. So similar to what we said before, we need to be careful about the conversion and the fact that on the layer 1 side in Solidity we have a Uint256, which is 256 bytes, but on the Starknet side we're working with the smaller data types. We have the felt 252, and so we need to make sure that what we have within our array of Uint256s is going to convert correctly and follow the serialization scheme that is being used. There's further details about that in the link given there. Another point you could get when calling from layer 1 to layer 2 is that when you want to call a function in a contract on Starknet, we need to effectively specify the function selector for that, because that is going to need to be found by the sequencer on Starknet. That function on Starknet in the Cairo contract on Starknet also needs to have the attribute added to it, the L1 handler attribute, to indicate that it is able to receive messages from the layer 1. Otherwise, it won't be able to be called. So you need to make sure that all of these, we are specifying everything correctly, the function selector is going to be correct, and that the function on the layer 2 is able to receive messages from the layer 1. The way that the function selectors are created is different to what you may have seen in Solidity, in that in Solidity we are using the first 4 bytes of a hash of the function name and the argument data types. In Starknet we have a felt 252, which is the selector is a felt 252, and that is a Peterson hash of just the function name. Again, going from layer 1 to layer 2, we need to be careful about authorization, and we need to be careful about the call up of the person who is sending the messages. So in your layer 2 function, it is almost certainly going to be the case that this function can only be called by a specific user, and so therefore we need to have checks in our layer 2 function that this is indeed the case, and that we have the correct user having sent the message from the layer 1. And this needs to be checked within the layer 2. Of course, we could have checks on the layer 1, but that could still mean that those checks could be bypassed by a malicious user. So we need to make sure in our function on layer 2 that we are doing sufficient checks on the address of the initiator of these messages. Yeah, and there's an example there if you would like to see more details. Now, looking at messages going in the other direction, if we have a layer 2 contract that would like to send a message to layer 1, then in order to do that, we use the send message to L1 syscall, and that needs to specify the contract on layer 1 that we are going to be calling, and then we need the payload specifying the details, the data that we're going to be sending to that. And the details that we provide are going to be the from address, so which contract on the layer 2 is sending this message, the to address, which is the address on the layer 1, address on Ethereum that we want to call, and then an array, which is the payload of this message. So the way that the messages are processed is a little different when we're going in this direction to when we're going from layer 1 to layer 2. And this is because the Ethereum contract on the layer 1 will call the consume message from L2 function of the Starknet messaging contract that is deployed on the layer 1. And if you think that every message sent to the layer 1 is going to be consumed, then that could be an incorrect assumption. So in this consume message from L2, what it specifically checks is that the hashes of the message parameters are stored in the call contract, and the layer 1 received message parameters are the same. And then the entity calling the function on layer 1 is indeed the one that we are expecting. Okay. Now, going back to the L1 to L2 direction, we do have the possibility where we can over-constrain this interaction, and the idea behind this is that you could have a contract on layer 2 which allows funds to be deposited on layer 1 and has some with the special function deposit to layer 1 specifying the address that this is going to be deposited to, and this will be used, for example, if you are burning tokens on layer 2 and showing that this should be transmitted to the layer 1. So the problem with this is if you do something like a burn, a traditional way of doing this is to specify a recipient address of 0, which is often regarded as an incorrect address, and therefore we could fall foul of the checks that are being done, where we're checking validity of addresses by seeing that an address is 0 and therefore thinking that this is an incorrect call to our function. Okay, so we could have the case that we are burning by sending tokens to the address 0, but on the layer 1 we have a check, we have a constraint that the address 0 is incorrect, and therefore we would revert this particular transaction. And so this produces, again, this is the problem with the idea of atomicity between the two chains. We would end up in an intermediate state where the tokens on layer 2 are seen as being burnt, and therefore we would expect to have some corresponding tokens on layer 1 being produced, with the typical kind of bridging behavior that you get between chains. But in this case, because the layer 1 thinks that address 0 is incorrect and has reverted, then we don't actually produce these tokens on the layer 1. So the user will lose their tokens on the layer 2, but not gain their tokens on the layer 1. Okay, so that's the end of Module 5 with examples of some vulnerabilities that you may find in your Cairo contracts. I hope you found that useful, and I look forward to seeing you all on Module 6. Thanks, everyone.